Let us take another problem. We want to determine the area of the region bounded by the curves x minus 2y square plus 2y equal to 0, it is given implicitly here, and x minus 12y square plus 12y cubed equal to 0. These are the two curves, and the lines y equal to 0 and y equal to 1. So, it is like whatever we have started in the beginning, it may look something like that. But then we have to first see how the curves should look like, whether there are points of intersection are coming those two exactly or something else. So, let us find the points of intersection of the curves. So, there the first curve we can write x equal to 2y square minus 2y, and the second we can write x equal to 12y square minus 12y cubed. So, eliminating x we get 2y square minus 2y equal to 12y square minus 12y cubed. Fine. So, now from this we solve for y, which gives that y equal to 0 or y equal to 1, because all that we want is in the interval 0 to 1 we only need it. Beyond that there can be, but we are not worried about that. So, in this interval 0 to 1 we have only two solutions of this, where y equal to 0 and y equal to 1. Okay. So, if you really plot them, it would look something like this. X equal to 2y square minus 2y is the curve on the left, that is blue one, and the magenta one is x equal to 12y square minus 12y cubed. So, you want to compute the area between them, where y equal to 0 and y equal to 1, they are exactly the points of intersection. So, giving that line is really superfluous here. We could have just asked determine the area of the region bounded by these two curves. Fine. And in the upper half plane. So, in the upper half plane only that is the region we would be getting. Okay. So, now how to get this area? You can in fact do in many ways. One is you can divide that into sub portions if you want to integrate through x, but here x is given as a function of y. So, it is quite natural to go the other way around. So, if you look at from the y axis, the pink one is on the top and the blue curve is on the bottom. So, then you can just write 12y square minus 12y equal to minus of 2y square minus 2y integral from 0 to 1, that would give the area of the region, right. So, you write that as the integral 12y square minus 12y cubed minus of 2y square, again minus of minus 2y, that is plus 2y. So, this is to be integrated. Fine. So, we know that 3y square will give us y cubed. So, 4 is remaining, 12y square as the integral as 4y cubed, 12y cubed as the integral as 3y fourth, and 2y square give y cubed by 3. So, 2 by 3y cubed, and 2y as the integral as y square. So, this we evaluate at 0 and 1, and we get finally the answer as 4 divided by 3. So, here you see the looking at from y axis, it became easier. If you do it from x axis, you can still do, but what you have to do, find this point and then subtract these two areas to get this area, and on the other side find this point and subtract this and this area, right, to get this area, the whole and minus this white. So, that is how also you can get it, but that will be a bit complicated. First you have to get these points, right. Okay. Let us take the next problem. Find the area of the region enclosed by the line y equal to x and the curve y equal to x square minus 2x. So, since it is enclosed by these two, it looks y equal to x should intersect that at least at 2 points, and then some region should be formed. So, this is how it looks. If you take y equal to x and then y equal to x square minus 2x on the downside this one. So, we have this region really. To get exactly what are those points where it intersects, we again solve the equations. We have x square minus 2x equal to y and x equal to y. So, x square minus 2x equal to x, that has solution as x equal to 0 or x equal to 3. So, we get the point x equal to 0 here and x equal to 3 here. And here y equal to x is on the top of the other curve y equal to x square minus 2x. So, it will be fairly straightforward to use the integral, convert it to integral. It will be simply integral of 0 to 3 x minus x square minus 2x. So, that gives x minus x square and this is plus 2x. So, you get 3x minus x square, right. It is 3x minus x square. So, 3x has the integral as 3 into x square by 2, x square as x cubed by 3. This has to be evaluated at 0 and 3 and subtracted. So, which gives the answer as 9 divided by 2. So, this was fairly straightforward, but you have to find the points of intersection first. Okay. So, let us go to exercise 4. We want to determine the total area of regions bounded by the line phi pi equal to x plus 6 and the curve y equal to square root of mod x. So, this square root of mod x, that means it will be looking like, if you use the definition of mod x, it is square root of x for x greater than or equal to 0 and it is square root of minus x for x less than 0 or even x less than or equal to 0. So, that is how the curve looks like. So, at least we have to consider two cases when x is positive and when x is negative, and then find the corresponding regions, add them up. Okay. So, let us take the first case, say x is greater than or equal to 0. In this case, we want to find the points of intersection. So, phi pi equal to x plus 6 and if you take phi pi there, phi pi equal to square root of x times 5. So, 5 root x and eliminating y, we get x plus 6 square equal to 25 x, that gives x square minus 13 x, right, x square plus 12 x minus 25 x. So, that gives 13 x plus 36 equal to 0 and if you factorize, that would give x minus 4 into x minus 9 and that is equal to 0 when x equal to 4 or 9. So, in this case, that for the positive after 0, if you choose any x, so it says that these two curves intersect at 2 points, x equal to 4 and x equal to 9. Similar thing might happen again on the negative side, right, when x is less than or equal to 0 or x less than 0. So, let us see that case. When x is less than or equal to 0, we have x plus 6 equal to 5 pi as earlier, but now square root of mod x becomes square root of minus x. So, again we try to solve it, squaring we get x plus 6 square equal to 25 into minus x or minus 25 x. So, we get x square plus 12 plus 25, that is x square plus 37 x plus 36 equal to 0. Again we factor them. So, that gives two solutions again, x equal to minus 1 or minus 36. So, that means when it is less than 0, we have minus 1 and we have minus 36. Corresponding to this, there will be points on the curve. And on the other side, we have 4 and also we have 9. Corresponding to that, somewhere they will be intersecting. Maybe this, we do not know where it is, but corresponding points will be there. That is what it says. So, you have to really find all the areas and then add them up. Okay. Now, we just look at something. We have, if x equal to minus 36, then y will be equal to square root of mod x, right. So, square root of mod x, or you can say from this also. So, that will be square root of 6 really, y should be equal to 6, fine. See, y equal to square root of minus x, mod x becomes minus x now. So, it is equal to square root of 36, which is 6. Okay. So, it gives 6 here. X equal to minus 36. So, y becomes equal to 6, but this is not possible. Why is it not possible? What is the reason? We will see from the plot what happens. If it is negative, then minus 36 is really a false point, which is not falling here, and all the other things we get your corresponding to minus 1, corresponding to 4, corresponding to 9. They are actually the points. Okay. So, we want to find out the area of these regions. Actually, we have only 3 points of intersection, not the fourth one. Okay. So, that is what we say, if x equal to minus 36, this will not be a possible solution, okay, because x is less than or equal to 0 and y becomes 6. So, we want to determine the area bounded by these 2 lines. So, there is no region corresponding to this binding the area, that is why it is not possible. Okay. So, only possible points are these where the regions are formed. Now, these are the 3 intersection points which correspond to x equal to minus 1. So, here is the intersection point, and x equal to 4, which is this intersection point, and x equal to 9, which is this. So, that means we compute the area which is painted black here. There is area of this area is clear, but the other area also is here, which is looking very small in the picture, but there is some area here. It is not a straight line. Had it been a straight line, its area would have been 0. It is not. It is really intersecting at 2 points, and there is some region formed. Okay. So, now how to compute the area of these regions? Of course, one from 4 to 9 will be straightforward. The top line which is straight line and bottom is the curve. So, we can just integrate it, but this one, the bigger black region has to be broken out again, right. So, let us say at 0 we break it, then we have one area which is formed, top line is the straight line and bottom was this curve, and on the other side again you have one on the top and one on the bottom. So, we have really got 3 integrals that way. That is what we do. Now, we break at 0 and write it as 3 integrals. One is from minus 1 to 0, where the line is y equal to 5y equal to x plus 6 or y equal to x plus 6 by 5 minus square root of minus x. That is the curve there when x is less than or equal to 0. And for the other integral, we have again straight line as the this area. So, there again straight line at the top and y equal to root x in the bottom. So, x plus 6 by 5 minus root x, and the other one, it is the straight line which comes below and the curve goes to the top of it. So, we have root x, x is positive. So, it is root x minus x plus 6 by 5, that is the integral, and the limits, one is minus 1 to 0, next one is 0 to 4, next one is 4 to 9. That is how we got the area to be written as sum of these 3 integrals. Now, if you integrate them and continue, simplification gives that the area is really 5 divided by 3. So, sometimes plotting may become necessary to find out what are the spurious solutions which are not forming the regions, bounded regions. So, like here it formed, it did not form any bounded region. Okay. So, let us go to maybe next problem. So, find the area of the region enclosed by y equal to secant square pi x by 3, y equal to x to the power 1 by 3, x equal to minus 1 and x equal to 1. So, these are 2 lines, vertical lines, x equal to minus 1 and x equal to 1. So, these 2 curves and these 2 lines. So, all that we have to find out which one is lying above what, and that would give us straightforward answer. So, now when it is x varies from minus 1 to 1. For this one we see that secant square pi x by 3 is bigger than x to the power 1 by 3. right. So, since it is bigger, we have the area as integral minus 1 to 1 secant square pi x by 3 minus x to the power 1 by 3 dx, and then you integrate. Secant square gives directly tan of this and pi x by 3. So, you have multiplied 3 by pi, and x to the power 1 by 3 gives 3 by 4, x to the power 4 by 3 evaluated at 1 and minus 1. So, that simplifies to 6 root 3 divided by pi. Okay. So, let us solve another. Let 0 be less than a less than b. So, there are two real numbers, positive real numbers a and b, where a is less than b. A1 is the area of the region bounded by the curve y equal to 1 by x and the lines y equal to 0, right, x equal to a and x equal to ab. So, one curve and there are 3 lines, y equal to 0 is the x axis and x equal to a, x equal to ab are the 2 vertical lines. Similarly, A2 is the region bounded by the same curve x axis, but now the 2 lines, vertical lines are different, they are x equal to 1 and x equal to b. We are required to find out which area is bigger than what, right. So, let us write them as integrals first. A1 is equal to, since the lines are x equal to a and x equal to b, it is integral a to ab, x to the power minus 1, that is 1 by x, the curve, and x axis of course below. So, y equal to 0. So, 1 by x minus 0, which is 1 by x, and A2 similarly equal to 1 to b, x to the power minus 1 dx. Now, you have to compare these two integrals and say which one is bigger or what happens. So, since the limits are a and a b, some a is multiplied here, we have to put a substitution. Let us put the substitution u equal to x divided by a. Here x is varying from a to a by b. So, if you take u equal to x by a, then when x equal to a, u becomes 1, and when x equal to a b, u becomes b. But in that case, what happens to the differential? You find that du here, du equal to x dx by a, that is what we wrote here, or you can write dx, which is dx equal to a times du. Okay. So, using that we get x inverse dx equal to u a, because x equal to u a to the power minus 1 and dx is a times du. So, a really gets cancelled, you get 1 to b, limits are for u. So, 1 to b u to the power minus 1 du, which again is same thing as, it does not matter which variable it is in the integral. So, 1 to b x to the power minus 1 dx, that means these two areas are same, fine. So, whether in that curve you take a to ab or 1 to b, those two areas will become same, that is what it says. Okay. So, let us stop here.